Ember training, platform overview, and support resources. So there are three different types of architectures that we generally talk about when we talk about Zigbee, and the one that's been around for the longest that you're generally accustomed to seeing in the market is the legacy design involving a microcontroller and what we call an RFIC, a radio frequency transceiver chip. So this transceiver chip is literally just a transceiver. It's not an embedded microcontroller. It's not designed to have programmable flash or anything like that. It's literally just a radio peripheral that requires an external chip to do anything useful. So this external chip would be some kind of microcontroller. Typically in Ember's history this has been a simple 8-bit microcontroller, but it could be something more sophisticated potentially. And this microcontroller would run the application software as well as the protocol stack software. So the remainder of the Zigbee stack that's not fulfilled by the transceiver functionality, the low-level MAC and PHY, if you will, the physical layer and the medium access control. So in these legacy designs, the disadvantage here is that the microcontroller has to handle a lot of additional overhead for stack functionality as well as managing the transceiver itself. The other problem here is that there's a fair amount of latency between what the microcontroller is doing and what the RFIC is seeing. So as the packets come up to the RFIC, they have to be passed over the SPI interface, handled by the microcontroller, and then any response that has to go back generally has to be sent back down through the RFIC and sent out again. So this introduces a lot of latency, and this is most apparent when doing things like security or encryption operations, where the RFIC typically can't decrypt the entire packet because it may need additional information that's only available through the microcontroller. So the encrypted data would have to be passed to the microcontroller, portions would be sent back down to any hardware encryption on the RFIC for decryption purposes, sent back to the microcontroller in decrypted form, and so on. So this design, while simple, is not terribly efficient and introduces a high amount of network latency to the system. It also doesn't give you a whole lot of flexibility on what microcontroller can be used because there's a lot of work to integrate this to a particular RFIC architecture. Now in contrast, around 2005, Ember introduced one of the world's first Zigbee SoCs, or System on Chips, and that was called the EM250. So the EM250 and our recently released EM35X platform, the EM351 and EM357 included in that, involves taking what used to be on that RFIC and moving it to an integrated peripheral inside the chip. So you're taking all of this radio functionality and you're designing it into the chip as silicon. So now you have one chip that can do all the transceiver functionality in hardware. All of the stack functionality can be handled on the SoC as well. And then the application can be linked against the protocol stack libraries to be able to interface directly with the stack functionality. So this provides a very nice unified approach where all of the firmware related to the Zigbee model is residing on one chip, so it's highly integrated. It reduces your cost because you only have to buy essentially one major component, which is this single chip, and then you just have maybe an external crystal to run that, and some capacitors and inductors and other sorts of things for your radio antenna structure, of course. But the primary cost here is coming from the chip. So by having one chip instead of two, the cost can be significantly reduced here. So in this model, you also tend to have the lowest power consumption because you have so few active components, and you also have much tighter control over what the stack is doing and when the application is interacting with the stack, because everything is literally residing on the same chip. Now the downside here is that because you have to share resources with the stack because you're running on the same chip, the application is potentially more resource constrained because it has to share processor time and share RAM and share flash with all of the stack functionality here. Okay? So for that reason, we offer a number of different offerings in the Ember family. The pre-existing model that existed since 2005 was the 200 series, the EM2XX series, and this comprised a 16-bit ZAP2B architecture. The ZAP2B being a core developed by Cambridge Consultants, which is a spin-out of Cambridge Silicon Radio, and CSR, Cambridge Silicon Radio, is the main designer of the majority of Bluetooth radios in the world. So that's where the ZAP2B platform came from, and that encompasses the EM250 chip. Now, the EM250, like all the SoCs, has embedded flash, embedded RAM, and in our architecture, it's also simulating EEPROM over a special section of the flash. So it provides 128 kilobytes of flash, 5 kilobytes of embedded SRAM, 17 GPIOs, and then there's about 8 kilobytes out of that 128K flash, which is simulated EEPROM for non-volatile storage. Then, on our newer series of chips, the 300 series, we have the EM351, which is based on the ARM Cortex-M3, a 32-bit ARM processor architecture. And that also has 128K of flash, although the code density is a bit different because it is a different architecture. It also has 12K of RAM and 24 GPIOs. The EM357 is essentially identical to the 351 with the exception of having a larger flash space. So it has 192K flash versus 128. So having released this SoC model, we shortly thereafter came up with a concept for a network coprocessor. So the EM260, which is also part of the 200 series family, is an offshoot of the EM250 SoC that's designed purely for coprocessor purposes. So rather than run the entire model of the stack from the transceiver functionality up through the stack libraries, up through the application all on one chip, here we're taking the stack functionality and separating it out from the application by moving it to a dedicated coprocessor. So this is different than the legacy design where the stack and the application shared a chip, similar to what they're doing in the SoC. And it's different from the SoC because the application is on a separate microcontroller. Okay? So now we have a dedicated application processor that can be roughly any kind of processor as long as it has a connection to the NCP. So in this case, we use a protocol called EZSP, Ember ZNet Serial Protocol, which is basically a serial abstraction of the stack libraries that existed in the SoC. And we communicate with the NCP via SPI protocol or UART protocol, depending on the sort of firmware loaded on the NCP. So using these common serial interfaces, you can have roughly any processor from, say, an 8-bit PIC all the way up to a sophisticated 32-bit or 64-bit embedded Linux gateway or something like that, being your effective Zigbee solution. So this adds Zigbee to a device in a fairly modular way where you may have an existing application architecture and you want to kind of modularly add Zigbee to that. So this is handy for that kind of approach. The other nice thing here is that because the stack data is all self-contained from the application, it's easy to maintain the stack functionality or upgrade the stack features without impacting the application or with minimal impact to the application, let's say. So, for example, the NCP could be a pre-programmed device that's sourced from a contract manufacturer and is preloaded, and then the application processor could then be customized further at the OEM's facility, at the manufacturer's facility. Okay, so it's a much more flexible approach. Now, the downside to the EM260, or rather to the coprocessor model, is that here we have two chips involved rather than one chip, so the cost is a bit higher. Now, the EM260 is cheaper than the EM250 because it doesn't have any GPIO, so it's a reduced function chip effectively in the sense of not having all of those I/O peripherals. Now the core is still the same, the memory architecture is still the same, so for all intents and purposes it's like an EM250 with no I/O, no user peripherals really other than that serial interface. Okay, so while it does save a bit of cost over the 250, you also have to make sure to save room in your BOM for this additional host processor, okay? But you're trading off for the flexibility of having a host processor that's decoupled from the stack architecture. And this allows you to kind of future-proof your design such that if Ember comes out with newer coprocessors in their offerings down the line and keeps the serial protocol the same, you don't have to change anything on your application side in theory. You just have to respin your board, your firmware at the application stays the same, and everything works out okay. So those are the three models that we provide. The legacy model, which we're currently not shipping or recommending in new designs anymore. The system-on-chip model, which is featured in the EM250 and the EM35X chips. And the Zigbee network coprocessor model, featured in the EM260. So now that you understand a bit about our platforms, let's just briefly look over the kinds of documentation that are available so that if you're going through the use of our stack or our kits and you need more help, you'll know where to go. So the right place to start is in the index.html file contained in the documentation folder of wherever you've installed Ember ZNet, your Ember ZNet root directory. And so that will link you to a number of things: the sample application descriptions, which can be found in their own index file, our application developers guide, which discusses the usage of some of these sample apps in more detail and their inner workings, a set of API guides, which are provided in Doxygen HTML format. So these document stack libraries on the single chip platform, the hardware abstraction libraries, and provided utility source code for sample code rather. And then in the EasySP cases for coprocessor installations, there's an EasySP reference guide that describes the EasySP command set, which will be similar to the stack API that's provided for the SoCs. There's also an application developer's reference manual. This is kind of a high-level document that describes the Ember ZNet architecture and the design of Zigbee and of our stack. And then you have application notes that detail more specific information about development and peripheral features, specific things in the use of the kit and of the chips. Then for Insight Desktop, which we'll talk about in detail later, we have a user's guide in PDF format as well as a context-sensitive online help. So you can click on different pieces of the architecture and find out how to use them. Then, with regard to our hardware abstraction layer, or our HAL, which is the interface between the hardware and the software or the firmware that abstracts the hardware design across different boards, all of that is provided in source code for you, and so there are header files there with comments in them, and the HAL API guide provided in HTML format should be able to walk you through that, but if you need the C code, that's there for you as well. Other resources outside of the documentation that comes with the kit can be found through our portal.ember.com website. So this is a universal developer portal for Ember customers and distributors and developers, which allow them to access FAQs, frequently asked questions, put up by experienced Ember FAEs. So this is information that you can depend on because it comes from a trustworthy source. And even that information is available without any sort of login. And then once you get a login to the site, which is restricted to customers and distributors only, you can download software updates and find out about more information regarding more specific topics within the system, release notes, release notifications, things like that. So if you are a current Ember customer, you purchased a kit, and you need a login to this page, please contact Ember via email at portal-logins@ember.com, and we can set you up with a new account. Remember to provide your 20-digit serial number from the kit that you purchased, as well as your name and company contact information, including email address. Beyond that, we have a support ticketing system, which is also access restricted, so make sure that you're logged in so that you can view this. And this allows online case tracking and case creation, which is handled through our global team of field application engineers, FAEs, as well as our support team. So again, you're getting authoritative responses from experienced Ember individuals. And that information, each of your tickets, is visible to a group from your company so that your development team can see all your tickets and nobody else from other teams, from other customers, can view your tickets unless you explicitly ask us to give those engineers access. Okay? So everybody who's working on the same project as you can monitor the issues as they're being dialogued with the Ember support team, but they're still restricted from access by other customers. And then we have a small blog going where our VP of Engineering provides updates about Ember engineering topics or Zigbee architecture topics, since our VP of Engineering is also the chairman of the Zigbee Architecture Review Committee. So those are a number of places where you can find different information regarding Ember's platforms and Zigbee information and that sort of thing. So we welcome your feedback. I'm Matt Dibb, and I hope you learned something.